Okay, let's unpack this. Time travel, just the thought of it, sends your mind spiraling, doesn't it?
It really does.
We're talking about potentially changing the past, which, opens up a can of seriously strange worms.
Definitely. But beyond the classic grandfather paradox, there's something maybe even weirder.
You mean the Bootstrap Paradox?
Exactly. It was where the usual rules of cause and effect seem to just, well, melt away.
Right.
Imagine something, say an object or information from the future, being responsible for its own existence back in the past.
A loop.
A loop, yeah. With no clear starting point, it really makes you question what we think we know about how things will happen.
Totally. And that's the rabbit hole we're diving deep into today, all thanks to the fascinating material you, our listener, sent in specifically looking at this concept, the Bootstrap Paradox.
Hmm.
Our mission, really, is to try and wrap our heads around this bizarre idea. What could it mean for our understanding of time, of causality?
Without getting lost in like super complex math.
Exactly. Keep it understandable. But what's fascinating, as you said, is this isn't just science fiction writer.
Not at all. While it sounds like something out of a movie, the Bootstrap Paradox is a genuine topic. It's discussed, debated within theoretical physics.
Okay, so this has real scientific grounding, potentially. So let's get straight to it. What is the Bootstrap Paradox in, simple terms?
Okay, so at its heart, it describes a causal loop.
A causal loop.
Yeah, think of it like an object or maybe a piece of information that exists, but without any obvious origin point.
How does that work?
It's as if it pulls itself into existence by its own bootstraps. That's where the name comes from. Its presence in the future becomes the very reason it existed back in the past.
Okay, wait, so it's a self-sustaining cycle, like a closed loop of cause and effect, but no beginning.
That's the core idea, yes.
That really throws a wrench in how I usually think about things. I mean, normally you expect a clear chain, right? A leads to B leads to C.
Exactly. With a definite starting point, A.
But this suggests something else.
Precisely. Our everyday experience is built on that linear understanding of causality. A causes B. The Bootstrap Paradox challenges that linearity, suggesting causality could be, well, circular.
Okay, circular causality.
Yeah.
So where does the theoretical possibility for something this strange even come from? It sounds more like a philosophical riddle.
That's where Einstein's theory of general relativity comes into play.
Ah, Einstein, of course.
Yeah. Certain solutions within his theory, believe it or not, actually suggest the possibility of these things called closed time-like curves, CTCs for short.
Closed time-like curves. Okay, that sounds significant. What exactly are they?
Imagine space-time itself, the fabric of the universe being warped or twisted in a really extreme way.
Okay.
So much so that it creates a loop. A CTC is essentially a theoretical path through this warped space-time that doesn't just move forward in time like we experienced.
It loops back.
It eventually loops back on itself, yeah, allowing something traveling along that path to potentially arrive back in its own past.
Whoa. Okay. So the shape of space-time itself could theoretically allow for backward time travel along specific paths.
That's the theoretical possibility, yes.
Yeah.
And the material you shared points to specific theoretical scenarios where these CTCs might exist.
Like where?
Well, one idea is around highly rotating black holes. The Kerr metric describes this. The intense gravity and rotation could twist space-time enough.
Okay. Intense gravity. Makes sense.
Another is a more theoretical construct called a Gödel universe, named after the logician Kurt Gödel.
The Kirk Biddle.
Yeah. He found a solution to Einstein's equations describing a specific type of rotating universe where these time loops are inherently possible.
Okay, my brain is definitely doing some stretching right now. The paper mentions this mathematical thing. Without getting too technical, what's that telling us?
Right. That equation. It basically describes the geometric conditions for a path through spacetime to be a closed time-like curve.
So it's the math defining the loop.
Essentially, yes. It involves how an object's velocity vector changes as it moves through curved spacetime. The key takeaway really is that if a path satisfies this condition and forms a closed loop, then you're on a trajectory back to your own past. It's the formal description of these self-returning paths.
Got it. So theory allows for these loops under extreme conditions, but still, how do we deal with the core weirdness, something creating itself? Seems impossible.
That's the crucial next step. How do you resolve the apparent paradox? And that leads us to the principle of self-consistency.
Self-consistency. Okay.
This idea is strongly associated with the physicist David Deutsch. He argued that if CTCs do exist, then any sequence of events occurring within them must be self-consistent,
Meaning?
meaning you can't create a paradox.
Yeah.
If you went back in time via a CTC, you couldn't, say, do something that would prevent you from going back in the first place.
Like the grandfather paradox, killing your
Yeah,
grandfather.
exactly. Self-consistency says that kind of outcome is impossible within a CTC. Everything that happens inside the loop has to fit together logically, without contradiction. The outcome must be consistent with the initial conditions that allowed the loop.
So the universe enforces consistency. The loop itself forces events to line up.
That's the principle, yes. The paper sort of hints at this with the idea that the probability of something existing at one point in the loop has to match up with its existence later, POT0, 0, T1, as it puts it, though we don't need the equation.
Right. The existence has to be consistent across the loop's timeline.
It's about the whole picture inside that loop making sense, being internally consistent.
Okay. That makes a kind of strange circular sense. If you're in the loop, what happens has to have happened to allow the loop to exist. Can we, walk through a simple example? How would this actually play out?
Yeah, absolutely. Let's use a classic example. Imagine an object, let's say it's a notebook containing instructions on how to build a time machine.
Okay, a time machine notebook.
Right. So at some point in the future, say 2050, you have this notebook, you use it to build a time machine, and then you send the notebook itself back to the year 2020.
Sending the instructions back.
Exactly. Now, back in 2020, your younger self receives this mysterious notebook. You follow the instructions, build the time machine, and you carefully preserve that notebook until 2050.
At which point I send it back to 2020.
Precisely. So the question is, where did the information, the instructions in the notebook actually originate?
Nowhere. It just seems to exist within the loop. It was sent back because it existed, and it existed because it was sent back.
That's the Bootstrap Paradox in action. No clear origin point. The information just circulates.
That is really weird. The paper gives that little equation for this, OT1, FOT2. Can you unpack that a bit?
Sure. It's just a shorthand way of saying that the state of the object, the notebook, O, at the earlier time, T1, when you received it, is determined by, or is a function F of, its state at the later time, T2, just before you send it back.
So the past state depends on the future state.
Yes. That dependency is what creates the circularity, the loop. O at T1 is what it is because of O at T2.
Wild. It feels like we're really bending the rules of reality here. Now, the paper also brings up entropy, the second law of thermodynamics.
Ah, yes, entropy, the universe's tendency towards disorder.
Right. Things generally get messier over time. How does a neat, self-contained causal loop fit with that universal trend towards messiness? It seems like the loop stays the same, right?
That is a really sharp question and a potential conflict. The second law says total entropy in an isolated system only increases or stays the same, never decreases.
Okay.
But in a Bootstrap paradox, if an object or system returns exactly to a previous state within the loop, its entropy within that loop might seem constant. The change in entropy would be zero because the entropy at the end point, ST2, is the same as the start point, ST1.
So ST2 minus ST1 equals 0, no increase in disorder inside the loop.
Potentially, for the object within the loop itself. That seems to clash with the usual forward march of time and increasing entropy.
So does that mean the paradox is impossible because it violates the second law? Or is there a workaround?
Well, the paper suggests maybe not. It hints that perhaps within these theoretical loops, there could be mechanisms we don't understand. Maybe interactions with the environment outside the loop allow the total entropy, loop plus environment, to still increase. Or maybe our understanding of entropy needs refinement in these extreme gravitational contexts.
So the loop might maintain its state, but the process of looping could still generate entropy elsewhere.
That's one possibility. Or perhaps entropy behaves differently under CTC conditions. It's speculative, but the loop itself doesn't automatically break thermodynamics if self-consistency holds. It suggests our standard view might be incomplete for these scenarios.
Okay, so even thermodynamics might get weird in a time loop. Let's circle back to the main issue, though. Cause and effect. That seems to be the absolute core of this paradox.
It really is. The Bootstrap Paradox hits right at the foundation. The principle that every effect has a prior distinct cause. Here, the cause and effect get tangled up. They become indistinguishable. The notebook exists because it was sent back. It was sent back because it exists. Which came first? There's no answer outside the loop itself.
It's its own cause and its own effect simultaneously.
Exactly. A causal circle rather than a causal chain.
And you mentioned the principle of self-consistency is the proposed escape hatch, the way to make this make sense without logic collapsing.
Yes. By insisting that any events within a CTC must be internally consistent, it sidesteps true paradoxes. Things can't happen in the loop that would prevent the loop itself. The universe in this view simply doesn't allow inconsistent histories, even potentially weird ones.
It demands a deterministic outcome for the loop.
A very tightly constrained, self-consistent outcome, yes.
Now, the paper also touched on something interesting, that information might behave differently than physical objects in these loops. How so?
That's a fascinating point. The idea is that information like the instructions in our notebook, or maybe, say, a poem or a song, might be even more amenable to these loops. Well, physical objects degrade. Entropy acts on them. But pure information, maybe not in the same way. Could a piece of information truly exist without ever being authored in the first place?
Like our time machine instructions, no inventor needed.
Potentially. The information just is, circulating eternally within the loop. Its origin isn't a single point in time, but the loop itself.
So an idea could just exist, temporally speaking, being passed around the loop without ever having a specific moment of conception. That's mind-boggling.
It really is. It suggests a possible nonlinear flow of information through time, maybe bypassing our usual understanding of how knowledge originates and propagates.
Fascinating stuff. And the paper, it gave a nod to some key thinkers who explored this whole area. We mentioned David Deutsch already.
Yes, his work on quantum mechanics near CTCs is foundational for the self-consistency idea.
And who else?
It also referenced Kurt Gödel, whose cosmological model first showed CTCs were mathematically possible within general relativity back in 1949.
Right, the Gödel universe.
And also Frank Tipler. He wrote a significant paper in the 70s specifically looking at CTCs and connecting them formally to the Bootstrap Paradox idea.
So this isn't just a fringe idea. Some real heavyweights in physics and mathematics have seriously grappled with it.
Absolutely. It has a solid history in theoretical physics, even if it remains highly theoretical.
Okay. So we've taken a pretty deep dive into this Bootstrap Paradox. If we had to boil it down, what's the main takeaway for our listener?
I think the fundamental takeaway is that the Bootstrap Paradox, whether physically real or just a theoretical puzzle, forces us to confront the truly bizarre implications of time travel.
Yeah, it pushes the boundaries.
It really pushes us to question our most basic assumptions about causality, about origins, about how things come to be.
And crucially, while it sounds utterly paradoxical, this idea of self-consistency offers a potential way out. A framework, maybe, for how these closed loops could exist without breaking physics.
Exactly. It's a mind-bending solution. But it suggests the universe might have rules that allow for things far stranger than our everyday intuition permits. Consistency might be the ultimate law.
Okay, so here's a final thought then, something to really chew on after this. If information can exist in a loop without a true origin, what does that mean for knowledge itself, for ideas? Could it be that some discoveries aren't new creations, but rather echoes? Information that has always existed, in a sense, just circulating in time until we tune into the loop.
That's a profoundly weird thought.
It is, isn't it?
Yeah,
Definitely something to ponder. And if you want to dig deeper, check out the work by Deutsch, Gödel, Tipler we mentioned. Lots to explore there. Until our next deep dive.